Hello everyone and welcome to this first year presentation on logarithms. So this is the starter that I'd like to do on a bit of paper please. And so what I'd like to do is to solve them, find the value of x that work for these equations, press pause on the video now, find those values of x, and then when you're ready for the answers, press play. Okay, good. So number one, x would be equal to 2 because 3 squared is 9. In number 2, x would equal 4 because 2 to the power of 4 is 16. On number 3, we have to start thinking about fractional indices. So 4 to the power of a half would equal 2 because a power of a half represents the square root. Number 4, we would need a power of x of a third because a third as a power represents the cube root, and the cube root of 125 is 5. And then finally, number 5, we find that there is a problem with number 5 because we don't get a whole number value for x like we did in numbers 1 and 2, and therefore at GCSE level you would use trial and error to find our value for x. And if you manage to get it to a value of 3.3 or better, then great stuff. But we need a better way of finding this value of x without using trial and error. And that's where logarithms is going to be handy. So this is a definition of a logarithmic function. If you'd like to write this down, please, in your notebooks and anything else that we see on this screen. So a logarithmic function is the inverse of an exponential function, very similar to how divide and multiply are inverses, sine and inverse sine are inverses, squaring and square rooting are inverses. Then an exponential and a logarithm are inverse functions of each other. So if I have my typical logarithmic function, and we would call this y equals log to base a of x, then the alternative way of writing it, the inverse function, is that x would equal a to the power of y. And this is the link between how the exponential and the logarithm are related to each other, and more importantly, how we can convert from one to the other. So using this conversion that you're seeing on the board now will be a way in finding the answer to that previous question in a lot simpler and a lot more efficient and a lot more accurate way than using trial and error. So the a value for both of these equations represents the base. A has to be a real number. A has to be greater than 0, and a cannot equal 1. So these are all caveats for the base number a. And the two most common base values that are used in logarithms are 10 and e. So log to base 10 of x, we usually denote as just log of x. So if we see log x written on its own, we can assume that they mean log to base 10. And log to base e of x, and we studied the e function in the previous presentation and looked at how special that function is in terms of exponentials. Log to base e of x is called the natural logarithm and is written as ln of x. And there is a button on your calculator specifically for the natural log of x, and next to it you will find the logarithm button that we use for any other base other than e. And we'll have a look at those in a few minutes. Okay, so going back to the question that we had in the starter where we had to use trial and error, there's a far better way of us being able to solve this equation and get a more accurate answer, and to do so more quickly as well. And the way that we're going to do that is to convert this exponential equation into a logarithm equation using that using the conversion that we saw on the previous slide. So if 2 to the power of x equals 10, using that conversion from the previous slide, we can rewrite it as x will equal log to base 2 of 10. So those two equations that you're seeing here are equivalent to each other. They mean exactly the same thing. They're just written in a different way. So the top equation is the exponential equation, and the bottom equation is the equivalent logarithm equation. And it's this one that we're going to use in order to find the answer to our question. So on your calculators, if you find your logarithm button, you should be able to input the base of 2 and to input the other value within the log function as 10. And then if you press equals, you will find that it gives you an answer correct to about 9 decimal places. So that would take you a long time if you were using trial and error methods, but we've now found it very quickly. And so I've rounded it off to 3 decimal places, 3.322. So what I would like you to do now, please, is I would like you to practice converting exponential functions into logarithm functions and finding the answer to those equations. So this would normally, as I said earlier, would normally have been done using trial and error, but if we can convert these exponential equations into logarithm equations, we can solve them quite quickly using the logarithm button on the calculator. So I shall give you as much time as you need to have a go at those 8, and then when you're ready to get the answers, press play on the video and I will go through them with you. Okay, so number 1, if we were to convert that into a logarithm equation, we would have x equals log to base 5 of 13. And if you work that out on your calculator to 3 significant figures, all of these answers 1.59. Number 2, log to base 2/3 of 9 will give us our answer of x, which is minus 5.42. In number 3, we would take 2 off the answer first, so take 2 off each side first before we get stuck into the logarithm. So 7 to the power of x would equal 8, and then we would do log to base 7 of 8 would give us our answer for x, which is 1.07. Similarly, with number 4, we can rewrite this as log to base 2 of 15 equals x minus 3. And then once we've got our value for the left-hand side, we just add 3 on to our answer and we get 6.91. Number 5, log to base 5 of 32 will equal 2x, and then divide both sides by 2 to get x, will give us 1.08. Number 6, log to base 3 of 43 will equal 2x minus 3. And then if you rearrange the equation by adding 3 and dividing by 2, we get 3.21. Number 7, log to base 2 of 52 will equal 3x plus 1. And then we simply take away 1 and divide by 3 to get x, which will give us 1.57. And then finally, number 8, it's a bit like number 3, get rid of the 5 first, because on number 8, the left-hand side does not equal 30 to the power of 3x minus 1 because of bodness. So the first thing you would do for number 8 is divide by 5, and then you would write log to base 6 of 16 over 5 equals 3 lots of x minus 1. And if you multiply out the brackets and rearrange by adding 3 and dividing by 3, you get a value of x of 1.22. So any problems with any of those 8, then please ask your classroom teacher for a little bit more support on those. Okay, so a little bit of experimental maths here now. What I'd like you to do, please, is choose a base number between 1 and 9. In fact, I wouldn't choose 1 because we've already said that the base number of a logarithm can't be 1. So choose a base number between 2 and 9 for me. And what I'd like you to do, please, is use the log button on your calculator to fill out this table of results. So I shall show you how I've done my first one. So I've chosen a base value of 3. So you can see that in my table, I've got log to base 3 of x, but you can choose any base number between 2 and 9. And what I'd like you to do, please, is I'd like you to fill in the table of results for these values of x. So for example, my first value will be log to base 3 of 0.25, which gives me minus 1.26. So we're working here to about three significant figures. And once you have found your values, what we're going to do is we're going to plot those values on the XY grid to look at what a general logarithm curve looks like. So do that now for me, please. And then when you're ready to press play again, by all means, let's go through what we've found out. Okay, good. So if I carry on my values, I get log to base 3 of 0.5 is minus 0.63. And if I carry on, you can see that by the time I get to log to base 3 of 1, I get an answer of 0. And you should have found that you also get log to base, whatever you've chosen as your base of 1 should also equal 0. So that's a rule that we will remember and write down in a bit. Log to base 3 of 2 begins to be positive, and you can see that if I plot these values as I go along, I end up with a shaped curve like you're seeing above. And if you were to plot your values, and by all means please do so, you should find that you get a similar looking curve as well. So it seems to be going through the x-axis at 1, and there does seem to be an asymptote at the y-axis. Okay, so this curve looks to be heading towards the y-axis, but never reaching it. And I could experiment with a few other values of x around the origin just to confirm that that is true. Now there is a definite link between the graph that we're seeing here and the graphs of those exponential functions that we were looking at in the previous presentation, but we'll discuss that on a future slide. So some general notes about the shape of a logarithm curve, please, which can be written in your notebooks. So if the value of a is greater than 1, which if you remember our base value was greater than 1 for the previous slide, then we have this general shape. The greater the value of the base, the quicker the graph decreases. And all log graphs of this form always cross the x-axis at the number 1. And that's something that we saw on our curve on the previous slide. If, however, the value of a is less than 1, so I'm talking here about a base value between 0 and 1, then the log curve has this general shape. And if you remember when we were doing our exponential work on the previous presentation, we had a different shape curve for when a was greater than 1 to when the value of a was between 0 and 1. And the same is happening here. We get a different type of curve. But no matter whether we have got a base value greater than 1 or a base value between 0 and 1, there is always this asymptote at the y-axis. And the final thing that we need to talk about is the fact when x equals the base of y, the value is always equal to 1. So our standard log curve will always pass through the point A1. So for example, if you want to write an example of that down in your notebooks, log to base 5 of 5 will always equal 1. Log to base 7 of 7 will always equal 1. Log to base a quarter of a quarter will always equal 1. So the log curve will always pass through the coordinate A1. And these are rules that we'll also look at on a future slide. So the next thing we're going to look at, which is a very important aspect of logarithms, is we are going to look at the laws of logarithms. And there are 5 of them that we need to find. And in the same way as we have laws of indices, and we use them quite confidently now, there are also laws of logarithms. So what I'm going to do to demonstrate those 5 laws of logarithms is I'd like you please to work out the values of these logs. So on your calculators, do that for me now, please. Of course, there is no base here, indicating that we're working in base 10. So find the values of these, please, and then when you're ready, press play again on the video. Okay, good. So log to base 2, 0.301, and we can work out all of the other log values using the calculator. And to 3 significant figures, we should find that these are the values that we found. Interestingly, before we move on, log to base 10 of 10 is equal to 1. We've discussed this before, that log to base a of a is equal to 1 every single time. So that holds true here. And then the 5 laws of logarithms that we need to look at are these 5 here. What are these 5 expressions equal to? So the first one, if I add together 2 logarithms with the same base, then I can combine them into one single logarithm using this rule. And to demonstrate that, let's have a look at just one example. So log to base 2 is 0.301. If I was to add on log 3, which is 0.477, then that acts in the same way as log to base 10 of 2 times 3. Now 2 times 3 of course is 6, and if you look at the value of log 6, you can see that it's the same as the values of log 2 and log 3 added together. And you can do that for other pairs of values that you see on this page. So for example, if you add together log 2 to log 4, you get the same value as log 8. If you add together log 4 with another log 4, you get the same as log 16. So there are various pairs of logs that you can use as an example of this. But if you add together 2 logs with the same base, then we can combine them by simply multiplying together the a and the b. Moving on to our second law of logarithms, we are taking the 2 logs away from each other, again with the same base. What would that equal? Well, again, I can demonstrate it using one of these or a pair of these logarithms that we've already worked out. So again, if I take log of 8 and I take away log of 2, then I achieve the same answer as log of 8 divided by 2, which is log 4. So if I take away log 8 and log 2, I get the same answer as log 4. And therefore the rule that we are using when doing that is that when I take 2 logarithms away with the same base, it creates a single logarithm where I have divided a and b. So again, there are other examples that you can use for this. So for example, log 6 take away log 3 is the same as log 2. And log 16 take away log 4 equals log 4. So you can almost think of it as the reverse of the rule that we found in the first law of logarithms. We then move on to our third law of logarithms, and we find that when we have log to base n of a to the power of x, it behaves in the same way as x times log to base n of a. So this is an example of where the power of the logarithm can come down to the front of the logarithm and act as a coefficient. So an example of that would be log of 16 is the same as log of 4 squared. And if I bring that power down to the front as a coefficient, then it can be written as 2 lots of log 4. And if you look at the value of log 4, which is 0.602, If I double it, I get the same answer as log 16. And there are other examples of that I can use, that you can see that rule applies in the same way. So this is a clever little rule where I can take that power of x and I can bring it down to the front as a coefficient, or vice versa. If I wanted to get rid of the coefficient, then I could take it up as a power within that logarithm. And we'll see some examples of that in just a minute when I come to solving equations that involve logarithms. And then our final two, we've already discussed the fourth one. Log to base of n is always equal to 1. The example that we've got here is log to base 10 of 10 is equal to 1. And then last of all, log to base n of 1 is always equal to 0. Doesn't matter what the base n is, log to base n of 1 is always equal to 0. And we found that out visually when we were drawing and sketching our log graph, in that our log curve, no matter what base we chose, always went through the x-axis at 1. So these are your 5 laws of logarithms. And you can write them down, please, in your notebooks and highlight them or put a bubble around them to indicate that they are important. And then on the next few slides, we will discuss how we can use them in order to solve equations. Good, so let's put those laws of logarithms to use then and try and solve some equations using them. So you can either have a go at these three on your own and then press play on the video once you've had a go if you feel confident, or you can stick with this and I will talk you through these three and then you can have a go at the questions from the textbook after that. It's completely up to you, but I'm going to go through these three now. Okay, so in number one, we have to find the value of x that works for this equation. So the first step I am going to use with question number one is I am going to use the third law of logarithms and take that coefficient of 2 up as a power. And the reason for me doing that is because what I want to ultimately get is a single log on the left-hand side and a single log on the right-hand side. And I'm not going to be able to combine those two logarithms on the right-hand side whilst there is still that coefficient of 2. So the most logical first step is to take that coefficient of 2 up as a power. And then once I've done that, I can then use my second law of logarithms to take these two logs away. And if we take these two logs away, as long as they have the same base, which of course these two logs do, log to base 10, then I can just simply combine them into a single log where the value of the log is 6 squared divided by 3. And then if I perform the maths on that, I end up with log x equals log 12. And then at that point, now that I have a single log on the left-hand side with no coefficient and a single log on the right-hand side with no coefficient, mathematically, it is logical to say that x must equal 12. So moving on to number 2, and in number 2 I have a different base. I have log to base 2, but that doesn't matter. The first step I am going to do is I am going to use my first law of logarithms to combine these two together. So I've got no coefficient, so it's okay just to simply add these two logs together and end up with log to base 2 of 5x. And then using my conversion rule, which is how I can change a logarithm equation into an exponential equation, when rearranged, I get 5x equals 2 to the power of 7. So that's using the skill that we were looking at in one of the previous slides. And then finally, if I work out 2 to the power of 7, it comes out as 128. And then if I divide by 5, I get 25.6. Now that's not the only way of solving that equation, but if you ended up with 25.6 as your answer, then you know you are okay with your method. And we will discuss other methods later on in another exercise. And then in number 2, I am going to have to find the value of x that works for these two exponential functions. So I am going to first of all take logs of both sides. It doesn't matter what base number I use, so I've chosen log to base 10. And then the reason for doing that is that I can then use my third law of logarithms to bring those powers down as coefficients. And you will notice that I've used a bracket on the right-hand side because that is important that we do. Otherwise, we're going to get confused using BODMAS. At that point, I can multiply out the brackets. That's perfectly okay to do in this case. So x log 5 plus 3 log 5. And then I need to isolate x. I need to find the value of x. So the clever way of doing that in this question is to take everything with an x over to the left-hand side, leave everything else that doesn't include an x on the right-hand side, and then take x out as a common factor. And you will see that by doing that, I've isolated the x, and therefore my final step is to do the division and end up with the value of x that I need. Now this is not going to be a whole number value or a pleasant decimal, so I've worked this out to 3 significant figures using my calculator, and I get an answer of 4.15. So there's 3 really good examples of how we can solve equations that involve logarithms, or we use logarithms to solve. So they are well worth having down in your notebooks and referring to when you come to do the exercise in the textbook. So it's your turn to practice now. So all those skills that we've learnt on the previous slides and some really good maths involved in those slides, we can practice those skills on page 86, exercise 3.1. Any questions, ask your classroom teacher, and then when you're ready to move on, we will have a look at some logarithms in more detail. Good, so moving on, there may be times when we have to change our logarithm into a different base. For example, if we're trying to solve an equation where there are different logarithms with different bases, we might need to change them all to have the same base. So there's a clever little trick to doing that, which we'll go through now, and you can write all of these notes down in your notebook, please. So we've already discussed the fact that these two equations mean exactly the same thing. They're just written in different forms. So the one on the left is your logarithm and the one on the right is your exponential, and one can be converted from the other fairly straightforwardly. So the version on the left we will keep as it is for now, and then the version on the right we will take logs of both sides. And I've chosen here log to base n. Of course, we could use whatever base we wanted to change our logarithm into. And then the logarithm on the right-hand side, we can use our laws of logarithms to bring that power down as a coefficient. And then that enables us to isolate y and get an equation that involves y. And now if we compare that to the original equation that we had in terms of y, we can now equate the two, and we can say that log to base a of x, which was our original log that we wanted to change the base of, can be written as log to base n of x divided by log to base n of a. And remember, we just choose the value of n that we want depending on the question that we've got in front of us. Okay, so here is another typical exam style question that involves us to find the values of x that work. And in order to solve this equation, I'm going to use logarithms to do so. So I'm going to show you the step-by-step process in which we would find the values of x. And the first process is to multiply all 3 terms in this equation by e to the x. And the reason why I'm doing that is because I want to get rid of that negative power of x. So here's my original equation here. This second term, an alternative way of writing it would be 2 over e to the power of x. So that would create a fraction with a denominator, and I'd much rather not have that denominator there when I'm solving the equation. So by multiplying all 3 terms by e to the power of x, it's going to get rid of that denominator, or if you'd like to think of it as getting rid of the negative power, then that is the purpose of doing that. So here is the result. So the first term will become e to the power of x squared. The second term will end up just equaling 2 because the denominator of e to the x has disappeared. And then the 3 will become 3e to the power of x. And my next line is where I'm going to bring all the terms over to the left-hand side and make it equal to 0. Because by writing it in this form, we are recognizing that what we've actually got here is a quadratic. We've got a squared term, we've got the x term, we've got the number on the end equaling 0. And although it's not a traditional looking quadratic, it's a quadratic nonetheless. And I'll show you how we can factorize this quadratic and then use the factorized form in order to find those values of x that I need. So my two brackets will both begin e to the power of x, and when I multiply them together, it will create the e to the x squared that I need. So my first two terms are e to the x, and then within the first bracket, I'm going to have minus 2, and then in the second bracket, I'm going to have minus 1. And you can see now that if I expand these double brackets, I will indeed get back to the equation above. So a very similar method to solving a quadratic. If you had your calculators, you could use your calculators to solve this quadratic. So you could put in values of 1, minus 3 and 2 for your values of a, b and c. And the values that your calculator give you would be values of e to the power of x. So there's an alternative way of finding these values of e to the x. But however you do it, you end up with two separate equations. The first of those equations is e to the x equals 1, and the second equation is e to the x equals 2. And if we can solve these two equations and find x, then they're going to be the solutions to the original equation. So the way that I'm going to find those values of x is that I'm going to rearrange these two exponentials into logarithm equations. And I'm going to use the conversion that we saw right at the beginning of the presentation. So if I do that, the first equation will become x equals log to base e of 1. And log to base e, if you remember, we call the natural log. And the second equation will result in an x value of log to base e of 2, which is the same as the natural log of 2. And then one final step before we've completed the question is that log of 1 is always equal to 0, no matter what the base. So x equals 0 will be our first solution, and x equals the natural log of 2 is our second solution to the original question. Okay, good. Time for you to practice those skills now. So there are two exercises. One is on page 87, one is on page 88. Have a go at these questions, and if there are any problems, please speak to your classroom teachers, and I will see you in a while for the final part of this presentation. Okay, good. So the last set of slides is using our skills of exponential and logarithm functions in context. So when would these functions be used in real life, and how can they be used to model certain real life situations? So I've got this question here, so pause the video, take your time to copy it down carefully. There are 3 parts, and I'll go through each of the 3 parts separately. And then when you are ready to go through the answers, then of course you can press play. We can go through each of the 3 parts. Okay, so we've got Emma. She's got a hot cup of coffee in her room. She places it on a table, and after t minutes, the temperature of the coffee is modelled by this equation. And you can see that this equation is an exponential function. We've got a negative power. We will have a look at what effect that negative power has. And we are also told that a and k are positive constants. And what we mean by that is once we've found the values of a and k, they cannot change. So constants can't change their value once we've found them. whereas T for temperature and T for time, they're examples of variables, and they can change depending on the values that we choose for them to be. But A and K are constants, and one of our jobs within this question will be to find the values of A and K. Now, in order to do that, we have been given an initial temperature, and that initial temperature of the coffee is 90 degrees Celsius. And we're going to use that in order to first of all find the value of A. Now, the word initial within this context is a really important word. So sometimes it will say initial or initially, sometimes it will say at the start, but it's an indicator that we are using a t for time value of 0. So when T is 0, the temperature of the coffee is 90 degrees Celsius. And it allows me now to create an equation where I substitute those values into the equation, which is what I've done here, as you can see. And the nice thing about this T value of 0 is that anything to the power of 0 is, of course, 1. So we can now start to develop this equation in order to find the value of A. So 90 ends up equaling 20 plus A, and therefore A is 70. And as I said before, because A is a constant, now that I've found that value of A, that is now not going to change its value. We now move on to part B. And part B gives me another temperature and another time. So we're now being told that it takes 5 minutes for the coffee to decrease in temperature from 90 degrees Celsius to 55 degrees Celsius. So how can I use my equation that I've just found in order to find the value of K? So we can replace that value of A that we found with 70. We can replace T with 5 because we're talking here about 5 minutes after the coffee has been made. And we know that at that time the temperature is 55. So there are 3 values now that we can replace within my equation, and that hopefully is going to allow me to find the value of K. So that's exactly what I'm doing here. I've replaced A with 70. I've replaced T with 55. And I've replaced small t with 5. And you have to remember that the e is a value. It's not a variable, it has a value. So the only value, the only letter that's left to find within this equation is the letter k. And I'm slowly going to rearrange this equation to find that value of k. So the first thing I'm going to do is get rid of the 20. So that's the easy step. I'm going to take 20 off both sides of this equation. The next thing I'm going to do is to divide by 70, which will give me 35 over 70, or a half, of course. And then the next step I'm going to do is where I take the natural log of both sides. And the reason why I'm taking the natural log of both sides is because then the natural log is going to cancel with the e function and just leave me with minus 5k on the right hand side. I'm then going to divide by minus 5 to get me my value for k, which nearly looks the same as the value for k that I'm being asked for, but not quite. And I've also written, as you can see, the number half as 2 to the power of minus 1. And then my final step to find k is to bring that power of minus 1 using my laws of logarithms, bring that power of minus 1 down to the front as a coefficient and create my final answer. So there's some good maths within this question that allows me to see those laws of logarithms and how the e and the natural log function are inverses of each other and can be used in order to cancel each other out. So a good question for part B, and then we'll move on to part C to finish off. So part C asks for the limitations of this model. So it's a nice way of showing how the temperature of the coffee is changing over time, but what. So the final part of this question, question C, is talking about the limitations of this model. In other words, how will this model fail in real life? Are there any factors that we haven't taken into consideration when we've developed this equation for temperature over time? So quite often, the model will fail when we are dealing with, for example, populations, because the model will indicate that the population is increasing, which of course can only happen up to a certain period of time. The population is not going to continue to increase forever. So this is what we talk about when we are describing the limitations of the model. So in this case, if we were to put in large values of time, we will find that this model, the value of temperature gets closer and closer and closer to 20. So the model is in essence saying that the room temperature is 20 degrees Celsius, because that is the temperature that the coffee temperature is heading towards. So there is an assumption that the room that we are placing our coffee in has a temperature of 20 degrees Celsius, which of course may not be the case. So that is the main limitation of this model, that there is an assumption that the room temperature is 20 degrees Celsius, when in actual fact it might not be. So that would be something that you can talk about if you are asked about the limitations of the model. Okay, and again, there is now a chance for you to practice these skills with these two exercises on page 90 and 91. So have a go at many of these questions. If there are any problems, speak to your classroom teacher, and then when you are ready to move on, then you could perhaps do the review exercise at the end of the chapter. But that completes our work on logarithms, and I look forward to speaking to you on the next presentation. Bye bye for now.